We're going to talk today about partial derivatives. First, by derivative, what we mean for now is a difference quotient, which means a rise over a run. So when we say in Calc 1, for instance, so let's talk about Calc 1 for a moment. Calc 1, the derivative is equal to 2. What does that mean? Well, it means that we have 1 unit over and then 2 units up. So this steepness is a derivative of 2. So that, as opposed to, or in comparing to perhaps a derivative of 3, if this is 1, 1, 2, 3. So again, this is a slope of 2. This is a slope of 3, or a derivative of 3. So that is steeper. A derivative of 1/2 would be something like this. So this is 1/2. So this is going to go more gentle, very steep, not as steep, but still steep. A derivative of 1, of course, will be a 45-degree angle, and so forth. So that's what we mean by derivative. Now, this is a derivative by itself. If we have a curve and we take derivatives at different points of the curve, then the derivative here, for instance, will be this much going down. Actually, yeah. And then what I'm trying to say is that things are going to fall faster the steeper this goes. All right, so this is a derivative here, derivative, derivative. And I'm thinking of it as falling using gravity. Okay, now, so this is the idea of derivative, geometric idea of derivative in a 1 dimension, well, really 2 dimensions. But what if we have 3 dimensions? So multivariable, multivariable, particularly in the case where we have 2 inputs, so f of x, y equals an output. Here, in this case, as we have one input and whoops, not equal, comma, equals 1 output versus 2 inputs and 1 output. So first, let me show you physically what is going on. Let's pretend you have a board. So this is just the back of some box that I found. And I'm going to tilt it. Hopefully you see it. And then I'm going to put a coin here. This coin is supposed to glide. There you go. So right now, let me change the angle a little bit. There we go. So let me increase the angle. There we go. So this coin will glide across the surface. It's taking me a little longer there we go, to get it just all right. Okay, so notice that if I keep doing this, placing the coin here, there we go. All right, so I'm going to do that a couple times. Notice that if I place the coin here and I don't move it, it will go in one direction consistently. See, it keeps going in the same direction consistently. But, so it's coming about this way. We end up here. If we start here, oh, I just changed the angle. Anyway, see, this is a box. This is just a regular box I found. And I'm tilting it in such a way that the coin will always come off on the same direction. But I'm tilting it from a corner. Oh, it's hard to see this. Let me use a real quick little cardboard. There, this is a cardboard, a little cardboard. So if I tilt it from the corner, the coin will go, there we go, this is much better, in the same direction no matter what. Okay, but that's, so we have a slope going down this way. But the way this is tilted, there's a different slope going this way and a different slope going this way, and the slope this way once it is tilted. See how it's going diagonally this way? It is why does the coin doesn't slide down on this direction? Because this is the direction of highest uh, or the biggest stiffness on this surface relative to the horizontal. So the coin keeps going always this direction. Why? Because that is the highest steepness. The coin is not going to want to go this way or this way because that is not as steep, even though we can go down. If I put some kind of block, let's say the pen, yeah, then the coin is going to want to go, yes, in the other direction because the pen is stopping it from going this way. That shows that we're going to go down no matter what, but this is the steepest way to go down. Of all the possible ways, there's many infinite directions. This is the way it's going to go steepest. So what does partial derivative do? The partial derivative, assuming this is, say, the x-axis, and this is the y-axis, x-axis and the y-axis, then the partial derivative is going to tell us the slope if we were going in this direction or if we were going in this direction. It does not tell us, the partial derivative, what the slope is going in this direction. That is going to happen in the next video, but not in this video of partial derivatives. So in the next video, we're going to talk about directional derivatives. So yes. So right now, let's talk about partial derivatives. So if you have some kind of surface and let's say the x-axis, so this goes down this way, there we go. So this is the x-axis, this is the y-axis. The partial derivative tells us the slope of the surface. Now the surface is tilted and there is a direction that gives us the steepest slope, but the partial derivative is not necessarily going to give us that. It is going to give us the slope in the x direction or in the y direction, depending on which kind of partial derivative we'll do. There's, in this case, two partial derivatives, x with respect to x and with respect to y, which means in the x direction and in the y direction. Is that going to give us the steepest of all? No, not necessarily. Maybe, maybe not. Depends on how the plane is tilted. But it is not going to be necessarily the steepest, and that's okay. It is good to figure this out. In fact, we're going to use those two to figure out the steepest in the next video, as I mentioned. That is if we have a straight surface. If the surface is not straight, yep, so there's the z-axis, the x-axis, and let's say we're at a point here, then we have different kinds of slopes, just like here, we have different kinds of slopes depending on where we are. This is going to be rolling up and down. And perhaps, for instance, here in the direction of the x-axis, we're going to have some kind of slope. In the direction of the y-axis, we're going to have a different kind of slope, perhaps depending on whether we're going to encounter a hill going up here on the right, or a hill coming this way towards us. Then we will have a positive slope. Otherwise, it may be going down, etc. How do we find partial slopes? Let me give you an example first. Remember, we did this in a previous video. We found the formula for a plane whose z-intercept is 5, y-intercept is 3, and x-intercept is 2. And that is 5 minus 5 over something x. So when x is, this is the number 2. Let me just copy it from my notes. Yeah, that way I'm not guessing. 2 minus 5 over 3y. So this is the same thing as the function f of xy. So if we said f of xy to be this z, which is that, we have this plane. Let's see, if x is 2 and y is 0, then the 2's cancel, and then we end up with 5, and 5 minus 5 is 0, so the z value would be 0, so we're good. Yep. All right, so this plane is this one represented in this picture. Let's label this as example 1. And the partial derivative, which is going to be denoted for now as z sub x, smaller x, means find the derivative of this, assuming that y is constant. So pretend y is constant. So the derivative of 5 is 0. Derivative of negative 5 halves x is negative 5 halves, no x. Derivative of this, we're assuming that is constant, so we end up with 0. So the partial derivative of z with respect to x is negative 5 over 2. That means that if you go at any given point here and you start going in the x direction, whoops, the slope is going to be negative 5 over 2, which makes sense because the rise is 5 and the run is 2. But if you go in the y direction, again, we start with this and we take the derivative of that with respect to y. So that is a little y, sub y. Derivative of z with respect to y means assume that the x is constant. So we end up with 0 minus derivative of this with respect to y will give us 5/3. So negative 5/3. And that makes sense because the rise is 5, the run is 3, as opposed to the rise of 5 and the run of 2. So 5/3 is the slope as we go in this direction, in the y direction. So we're assuming this point is here, an arbitrary point, and then we're going, again, this direction, and here we're going in this direction, in the y direction. And that's how we obtain the partial derivative. Let's do a second example. Example 2, let's say f of x, y is some kind of polynomial, let's say 3 plus 4x plus 5y plus 6xy plus 7x squared y, just to give an example. So we have 1, 2, 3, 4, 5 terms in this example. So the derivative f sub with respect to x, so f sub x of that is, okay, so we're going to assume that all the x's are variables and all the y's are constants. So this is constant already, so 0, plus the derivative of 4x is 4. This we assume is a constant, 0. Okay, the x is variable, the y is constant. So this is the only thing we're derivating, x. The derivative of x is 1. So this is really 6y because the other two are constants. Here, the variable is x. The other items are going to be constants, 7 and y. The derivative of x squared is 2x, but then we have 7y with it. So we're going to have 14x. And then the y. 7y is the constant times 2x, and that gives us 14xy. So let's simplify this as 4 plus 6y plus 14xy. So this is going to be some kind of surface in 3 dimensions, and this is the derivative at any given point if you go into the x direction. But if you go into the y direction, the answer is going to be different. The derivative of f with respect to y, starting with this one, the derivative of 3 is 0. The derivative of that is going to be 0 again. because we're assuming y is the variable, and anything that is not y will be a constant, will be considered a constant. Derivative of 5y is 5. Here, the y is the variable, so 6x is constant. Derivative of y with respect to y is 1, so we end up with 6x, plus the derivative of y again is 1, so we just keep the 7x squared. Simplify that as 5 plus 6x plus 7x squared. So this is the derivative. Well, okay, starting with this function, this is the derivative with respect to x, and this is the derivative with respect to y. And that gives us partial derivatives. Those are called the partial derivatives. I have not defined formally what they are because the derivative includes limits. For purposes of this video, we want to become more operational, even though there is value in knowing the definition. The definition is based on limits, and it is very straightforward, but I'd rather spend more time on how we actually go about getting the derivatives. So those are the way we find partial derivatives. Practice the partial derivative because it does take a little bit of getting used to it. Let's do another example, a simple example, example 3. If f of x, y is, say, x over y. Okay, that's already a little confusing. So the partial of x with respect to, rather, the partial of f with respect to x. So x is the variable, y is a constant. So pretend this is x over 7. The derivative of x over 7 is 1 over 7, or in this case, 1 over y. Not to be confused, so we're not using the quotient rule whatsoever. And if you did use the quotient rule, if you wanted to, then you got to pretend y is a constant, and it will still end up being the same answer. Very inefficiently if you use the quotient rule, but you could. Partial with respect to y. Now, sometimes we omit, if it's understood, the x and the y. So since I'm running out of space here, I'm going to omit that. So again, x is the constant here. So these are three different things. This is the original function. This is the derivative with respect to x of the original function. And now we're going to write the derivative with respect to y of the original function. So the original function is this. We're assuming y is a variable, x is constant. So the x is going to be preserved. The derivative of 1 over y, so I'm assuming there's no x there, just for purposes of figuring this out. I know well that the derivative of 1 over y is, with respect to y, is negative 1 over y squared. Negative 1 over y squared. X is just a constant for the time being, so we just place the constant there. So there is no big drama when you're trying to find partial derivatives. Please don't dramatize it because it's not that difficult if you know how to do derivatives already. Yeah, you just gotta get the hang of it. Notation. It is my view, my personal view, that the more people who put their hands into a topic, the more variety of notation will come up because everybody's going to have their own notation. They're going to try to influence it, influence the topic by their own notation. And it's not that they try, it just happens. Anyway, so because a lot of people use partial derivatives, there's, in my opinion, this is my opinion only, many ways to write partial derivatives. So one way, which I already explained, is f sub x, the partial derivative of f with respect to x. It doesn't matter whether you put the inputs or not. There it is. So those two are the same thing. Another notation is d sub x, so derivative with respect to x of f. And you can put the same thing with the variables or not. And there is another notation which uses this symbol. It's like a bent D. I call it partial derivative symbol. So partial derivative of f with respect to x. So that is another symbol we use. and you can put the inputs if you want to. So it's not a regular D, it's a bent D. That's the same thing. And you can use it as an operator. So this is again that D with the bent stick. So you can put the F on front, and you can have it um, F of X, Y. There we go. So there's a few different ways to write the partial derivative of a function F with respect to X. The same thing will happen with Y. So there's a number of ways of doing this. If you have more than two variables, you can have functions of 3 variables, 4 variables, 5 variables, any number of variables. So more variables, no problem. So as an example 4, let's say you have a function of x, y, z, w. So this lives in 5 dimensions, 5, because there is 4 inputs and 1 output. So I'm not even going to try to draw anything like this, but let's say you have 2xy plus 3zw, or there's going to be a bunch of different ways of combining the x's, the y's, and the w's for, let's just do one more xw. There we go. And there could be more, and there could be sines and logarithms and other things. Anyway, if you want to find the partial of the function with respect to x, treat everything that is not an x as a constant. So the derivative of x is 1, so we just end up with 2y. That has no x, so that is a constant. That derivative is 0, plus the derivative of x is 1, so treat the other two as constants. For w, we're set. So that is the derivative of f with respect to the partial derivative, partial mind, of f with respect to x. Yep, yep. So that means that is as x increases, the output of the function is going to change relative to y and w. And that means that z has no effect on the output if you go in the x direction. Yeah. Yeah, try to understand a little bit of what the equation means. Yeah, so this means that, again, the output, the derivative of the output going in the x direction is relevant to, or is related to y and w, not x, not z. We can have second, third, fourth derivatives, second, third, fourth, etc. derivatives. Yep, many derivatives of a function. Not only that, not only we can have a more than one derivative, we could have mixed derivatives. So let's take a polynomial, well, a monomial that is fairly large. Let's say you have, so this is going to be example 5. Let me double check. Last one was example 4. Yep. So let's say you have f of x y equals 7x cubed y to the 5. There, just one term. But the exponents are high enough so that it will withstand, excuse me, many derivatives of different kinds. So the derivative of this function with respect to x is going to be, of course, okay, so the derivative of this guy, the x cubed, will be 3x squared. But then multiply that with the 7, that gives us 21x squared. And then we keep the y to the 5 because that is a constant. Not to be confused with the derivative with respect to y. Okay, so with respect to y, pretend the other two are constants. So we end up with 5y to the 4 the 5 multiplies with the 7. So we end up with 35 x cubed y to the 4. We can do a second derivative with respect to x. So derivative with respect to x, and then derivative with respect to x again. So take this guy, and then do the derivative with respect to x. That would be a second derivative. So x, derivative of x squared is 2x multiplied with 21, we get 42 x y to the 5. We could also do f sub x y. So derivative of x first, and then derivative with respect, derivative of f with respect to x. After that, derivative of what we just found with respect to y. So starting with this, which was the derivative of f with respect to x, find the derivative of that with respect to y this time, and that's going to give us 105 because we're doing the derivative of just the y. So 5y to the 4, but the 5 multiplied with the 21 is going to give us 105 x squared y to the 4. All right. Or we could do f sub yy. So start with a derivative with respect to y, and then find the derivative of that with respect to y again. So we just look at this guy, and we end up with 4y cubed. So 4 times 35 is 140. Keep the x cubed, y cubed. Or we could do f yx. So start with this guy. So let me draw an arrow. This came from here, and the new one is going to come from that too. And do the derivative of this with respect to x. So we're going to multiply 35y to the 4 with 3x squared. So 3 times 35 is going to give us 105 x squared y to the 4. Notice that those two are the same. I'm going to circle them. This guy turns out to be the same as that one, and that is no coincidence. However, the way we came up to those two is different. This 105 came from 35 times 3. This 105 came from 21 times 5. So watch out. We do end up with the same answer if you mix them. Most of the time, I shouldn't say it all the time, there's a theorem that tells us that one we should write down. Clairaut's theorem states that if things are nice enough, and most of the time things are going to be nice enough, so on the right, okay, so under, this is very informal, under nice conditions, fx sub y is going to be the same as fy sub x. Yeah, so this is very informal. And it's okay to be informal sometimes, not all the time, of course. Especially in mathematics, we should be formal. But at this point, when we become too formal in one direction, then we lose track of what we're doing. So be aware that if we have nice conditions, then this is true. By nice conditions, we have to have continuity. Things cannot be on the edge or the boundaries of domains where things start getting weird. So for instance, if you have a tangent function somewhere involved in this picture, everything is going to work well as long as you stay away from where the tangent changes, for instance, or the secant, or the logarithm, where things are going to be really, really weird. I just want to remind you what the tangent looks like. Tangent. graph. So we have asymptotes, then we got something like this, and another graph like that, and this is going to be pi over 2. So as long as we stay away from pi over 2, um, things should work really well, and this continuity here, and then we are going to have continuity of the derivatives. Or also, if you stay away from cusps, sharp corners like a V, yeah. So everything is going to be okay here, okay there, okay. But we will have a problem on asymptotes, or when we have a sudden change of direction. That's when things could get bad. Um, so just be aware of that. That's what I mean by nice conditions. Yeah. And again, this is very informal. I'm being informal on purpose. So Clause's theorem says that if you do one way or the other, many times under the nice conditions, if we're not looking at a particular problematic point, we're going to be okay. If things are smooth, yeah, nice conditions, smooth. If the surface is smooth enough, then we don't have to worry too much about things. Yep. Nothing stops us from having third derivatives or fourth derivatives and combination of third derivative and fourth derivatives. The notation has to be spoken about. So fxy will mean first x and then y, not to be confused with the partial derivatives. So the second partial derivative with respect to y, x, yeah. So when we're using partial derivatives, we go in this direction. First derivative with respect to x, then derivative with respect to y, versus this notation. So when we are using this notation, we go from left to right, first x, then y. When we use this notation, first x, then y. They're the same thing. Oh. And then we have dxy. So all of them are the same. All of these are the same. Oh, I guess I should use f if I already used f there and f here. Yep. So just be aware of the different notations and the direction in which we use the notation. So this one goes backward. And the reason is because we are, okay, let me show you why. So if we have f and you apply x derivative partial of f with respect to x, then applying y means this, and then you can just put them together in a chain. As opposed to applying to f the partial with respect to x, and then when we apply that, because the function is on the right side, we apply the partial, whoops, this is a partial with respect to y after on the left. So those two are equal. And then the same thing happens here, d sub x. Ooh, that gets complicated. F, oh yeah. But then we got to apply d sub y. Whoa, yeah, d sub y of d sub x. So I guess this kind of looks, because those are two d's. We're going to take we're going to assume that dxy means that direction. But if you have the d's in this order, then things may be different. At some point, it will make a difference whether you do these in one order versus the other order. Yeah, it does make it can make a difference in some scenarios. Before we finish this quick section of partial derivatives, or this quick video of partial derivatives, let's talk about antiderivatives. Antiderivatives. Okay, so antiderivatives, as you know, is, well, an antiderivative. So in Calc 1, if we wanted the antiderivative of x with respect to x, well, the answer is, of course, x squared divided by 2 and add the generic constant. But in multivariable calculus, the antiderivative of x with respect to x, assuming that we have two variables, x and y, it's going to be x squared over 2, yes, but, so this is under multivariable calculus, and assuming x, y are independent variables, inputs, then the constant is not just a constant, it could be any function of y. So we usually write down c of y, where this guy is any, and I mean any function of y. Yeah. Let me just do a quick example of this. So what example number will that be? 6, about antiderivatives. Example 6. So Calc 1, antiderivatives of x squared, rather of x, will be x plus 5, x minus 7, x plus pi, x minus 13, etc. Those are the antiderivatives. There's many, many millions more. And the generic way to write this is just x. Oh, I meant x squared over 2. Silly me. I get sometimes too excited about something and then I start losing a few. Sorry to do this to you. So x squared over 2, this is the antiderivative, plus a generic constant, where the constant could be 5, 7, pi, negative 13, negative 7, whichever. So this is the way we write the antiderivative of x in Calc 1. But in multivariable calculus, and we have to be specific with x and y, because we could have x, y, and z. What is the antiderivative of x? Well, it could be, we could have x squared over 2, just like we did up here, plus y squared, or x squared over 2 plus sine of y, or x squared over 2 plus tangent of y plus 3, or x squared over 2 plus e to the y minus 7 sine of y plus 5, etc. So we still have the same root, x squared over 2, just as we did here. The difference is that we could add any constant because the derivative of a constant with respect to x is 0. So we're not going to get back anything other than the x. But in multivariable calculus, the derivative of y squared with respect to x is going to be 0. So we could have any function of y and still end up with 0. So be aware of the antiderivative. In general, all of this will be represented, and there's many, many, many more of those, will be represented with x squared over 2 plus a function of y, a generic function of y. That function of y may have constants or not constants in it as terms. Yeah. So going backward can be complicated. And just one more example. Well, this is the same general example. So let's say you have a multivariable calculus and you got 3 inputs, x, y. So with x, y, and z, what is the antiderivative of x? I'm not going to give you many examples. I'm just going to say it could be of x squared over 2 plus a function of y and z, which could be broken up into more than a function of y, a function of z, and a function of the actual combination of the two. So a generic, this can get more complicated because you can have just y, just z, or a combination of terms. All right, this is it for partial derivatives.